Let's look at the limit of a power function as x approaches infinity. Power function that's a polynomial. For example, suppose you have f of x is equal to x to the power of 2, and you want the limit as x tends to infinity. Well, if you do it by substituting infinity here, all you would have is infinity squared, which is infinity, although infinity is not a specific number. But what this is saying is that as x gets infinitely large, x approaches infinity, the value of x squared will also approach infinity. As x gets infinitely small, then I can tell you that x will approach infinity as well. Because if we try, for example, when x equals 5 right here, then f of 5 is going to be 5 squared, which is 25. So when x is 5, then y is 25. When x is negative 5, say x is negative 5, and negative 5 is right here, then what you have is negative 5 squared, which is 25 again, somewhere here, right? But I can tell you, if you plot the graph point by point, you're going to get something that looks like this. Anyway, let's look at the graph here. We have x to the power of 2. Aha, there we have it. And as you go more and more to the right, you see values to the right. What happens to the values of x? They keep going up and up and up with no end, right? It's a never-ending growth, and it grows very, very fast. And as you go to the left, x also keeps going, the value of f of x. As you increase the values of x to the left, the values of f of x rise rapidly. After a while, they go up really rapidly. Right? Upwards. So, what you have here is the limit of a polynomial, and the limit of f of x squared is infinity. As x tends to infinity, the answer, when you work it out, also goes to infinity. Alright? Now, let's look at another situation. If we look at y equals, no, f of x equals x cubed, what will happen? Let's change this to x cubed. Let me erase. Let's change this graph to x cubed. X to the power of 3. You see what happens here? When you have x equals, say, 0.5, x is 0.5, right here. When x equals 0.5, f of x will be x cubed 0.5 to the power of 3, which is 0.5 by 0.5 by 0.5. So you have 0.5 by 0.5. It will be half by half by half. Alright? Half by half is a quarter, so it's a quarter by half. So 4 2 is 8, 1/8. Right? So when x is 0.5, this is 1/8. Now, what happens when x is negative 0.5? What you will have is when you have negative 0.5 for x, you have a negative 0.5 cube, which is negative 0.5 by negative 0.5 by negative 0.5. Same thing as negative half by negative half by negative half. Negative half by negative half is a positive quarter. But you have a positive quarter times negative half, we give you negative 1/8. So the 1/8 comes this way this time. But at the same time, you will see that as the values of x increase to the right from 0, the values of f of x increase towards infinity, become infinitely large. As x becomes infinitely large, the values of f of x become infinitely large. As x becomes infinitely small going to the left, right, the values of f of x also become infinitely small, just like how these shoot up and become infinitely large. These on the left shoot downwards and become infinitely small. So again, in this case, the limit is negative infinity, right? So what you can say about this generally is that the limit as x tends to infinity of a function x to the power of a number, say n, the limit of that is equal to, it might be negative positive infinity or negative infinity, right? Generally, you might see a k x to the n. Let me rewrite that k. You might see a kx to the n there. In some cases, the k is just a number. For example, if I should take this function as it is, y equals x cubed, and multiply x to the power of 3, and say I multiply by 3 times x to the power of 3. I want to plot another graph. Let me get rid of this one. Okay, good. Or it could be 5 times x to the power of 3. Same shape, same behavior. It could be 5 times x to the power of 2. So in this case, I use 5 as my k. So long as you have a number, multiply by x to a power, it takes this same behavior, any number you have times x to the power. Alright? Now, suppose you have another case. Let me erase these and look at another case. We started out with x squared. If we have a case like x to the negative half, which is the same as 1 over x squared, right? Then what would happen in this case? Let's change this function to 1 divided by x to the power of 2. Okay, now you see what happened there. The lines of the graph get closer and closer to 0, but they never reach 0. That is, as you approach 0. However, what we're looking at is x approaching infinity and negative infinity. Now, as x goes to positive infinity, the line on the graph gets closer and closer to 0. As x goes towards negative infinity, the line or the curve gets closer and closer to 0. So therefore the limit as x tends to infinity of f of negative of f of x, in this case, not just generally f of x, of x to the power of negative n. And we could put a k there. K, any number times x to the power of negative n is equal to 0. Because guess what? You see, for the x squared, when you put 1 over a very big number, you get a small answer. For example, suppose x was 5. Then 1 over 5 squared is 1 over 25. Quite small. What happens when x reaches 100? Then 1 over 100 squared is 1 over 10,000, which is extremely small, getting smaller and smaller. It's approaching 0. So, as x increases, f of x gets closer to 0. Alright? So now, what we can say is that the limit as x tends to infinity of a number k over x to the n is equal to, it can be positive or negative. No, not positive or negative, it's just 0. Alright? It doesn't make sense to say positive 0 or negative 0. It approaches 0. The answer approaches 0. The limit approaches 0 as x increases. Now, there is one particular case we want to look at before we finish. Or rather, two cases that we want to look at before we finish. Suppose in this case, we have the limit as x tends to infinity of x to the power of a half. In other words, if you remember, you have to remember your indices. This is the same as the square root of x. Now remember, you cannot find the square root of a negative number. Alright? So let us see what's going to happen in the graph of this. When you plot the graph of this function, what do you get? X to the power of alright, 0.5, same as the square root of x. Now you see that there's a plot. It's plotted on the right hand side only, because the left hand side has negative values. Alright? But what we're looking at is what happens as x increases towards an infinitely large value. X approaches infinity. What happens to f of x? The answer when you work it out. Well, in this case, let me zoom out. It's increasing, but increasing at a slower and slower and slower rate. Alright? As you zoom out, it's increasing slower and slower and slower. You can see that. Now in this case, it might seem as if f of x is approaching a particular value. Well, let's look at it. What we're looking at is f of x equals square root of x. Now, If x is 100, then what we have is f of 100 is equal to the square root of 100, which is 10. What about what happens when x reaches 10,000? The square root of 10,000 is beg your pardon. We want the square root of 10,000. So things are getting in the way. Okay, 100 equal, you have 100. What about the square root of 1 million? Square root of a million. 1 and 6 zeros. 1,000 is still increasing. What about the square root of 100 million? It is 10,000. So it is indeed, f of x is indeed increasing. It's just that it's increasing at a slower and slower rate, but there is no particular value that it will reach. So in this case, the limit does not exist, right? The limit is getting at or rather, let me say, the limit is approaching infinity. As x tends to infinity, the limit of the square root of x is approaching infinity, but at a slower and slower rate. Because if you increase the value for x to millions, billions, trillions, you'll get an increasing value for the square root of x, and there is no limit to it. Alright, there is no stopping. There is no particular value that it gets closer and closer to, and then we could say that that's where it ends. Alright, now we'll continue looking at limits in another video.